Hey, so we've been looking at our batteries, our voltaic cells. Now we can start to actually split those two half reactions into different containers to be able to send those electrons through an external wire to actually be able to do something with that energy, those electrons as they flow from anode to cathode. Just a couple of reminders here. Wanted to do a little bit of review and also kind of layer in that last little piece that we need when we start to talk about these cells, these batteries, if you will. Just quick reminders as we start to think about our terms and our different locations. Anode versus cathode. Anode, anions, negative. Cathode, cations, positive. And so for your anode, this is your electrode where the oxidation will always occur. It doesn't matter which type it is, whether it's voltaic or electrolytic. This is where your oxidation is going to occur, where you're going to be losing your electrons. This is where you're going to lose mass. This is the electrode that's going to get lighter over the course of the reaction. And this is the electrode that attracts the anions from the solution. So this is where we're starting to think about our particles and think about what's happening. For our cathode then, this is where our reduction occurs, where we're going to be gaining the electrons. The electrons are always going to be flowing towards the cathode. Our electrode is going to gain mass at the cathode. This is the one that's going to get heavier over the course of the reaction. And this is the one that attracts the cation. So when we're thinking about what's actually happening to the particles and which direction things are flowing in terms of in versus out, this is kind of a good reminder, good refresher as to what's happening at our two electrodes, at our anode and our cathode. And cool, so we can actually start to kind of diagram or describe what's going on based upon the different particles taking place in our electrochemical reaction. That's kind of our next piece to this puzzle. So if we're thinking about kind of this is our go-to zinc and our copper, and we're thinking about how from our anode, our electrons are flowing away from the zinc. So electrons are flowing up through our zinc anode, through our external wire back over to our cathode. When that happens, our zinc loses 2 electrons, pops off then as a copper 2+ ion, increasing the positive charges in the solution. More and more zinc ions are popping off into the liquid. If we have too many zinc ions build up, if the positive charge builds up too much, our reaction is going to stop. And that's why, for this example, our sulfate, SO42-, comes down in the salt bridge to keep the ion solution neutral, keep it the same. As those electrons travel through the external wire to the copper, well, now our copper 2+ is going to come up to this cathode. It's going to attract that positive, and that ion attracts to the copper. That electron flows down, the copper comes in, and we end up plating onto our cathode. And so if we're thinking about our overall reaction, here's our overall reaction. Then for our half reactions at the oxidation, we got our zinc breaking apart into zinc 2+. At the reduction, or at the cathode, we got a copper 2+ gaining our 2 electrons. Here's what's happening in our 2 kind of chambers. Well, it turns out as chemists, we've got kind of a shorthand. And that's kind of the new piece that I want to talk about today and look at some review. We've got a shorthand way of showing this. We call this our cell notation. We really want to know what is happening in our 2 beakers. Kind of a snapshot of what do we need to build this. If we actually want to make this happen, what would we need to do? And so what we do is we kind of have this shorthand way of writing this. We're going to put our components of our anode or oxidation half reaction, what's going on in the anode side. On one side, the double line here represents our salt bridge or our divider. On the other side, we got our cathode. Well, what's going on in the cathode over here? Well, in the cathode, we've got a reduction. So what's going on in those 2? So the way we write this by convention is we go our lower oxidation number to higher oxidation number in the oxidation or the anode side. And then we go higher oxidation back down to our lower oxidation numbers. This is based on the oxidation state or the oxidation numbers. The way I remember is if you're familiar with the old Price is Right theme song or the Price is Right game where the little climber, right? Low to high to low. So you kind of climb the mountain and then come back down. Low to high, high back to low. And this makes sense if we're thinking about the electrons. Our zinc is our lower oxidation state, 0. It's going to 2+ and giving away 2 electrons. So it's going from zinc to zinc 2+. And then in the other beaker, our 2+ is gaining it, going back down to 0, going back down to copper. And so we're just describing in a snapshot what's actually happening, what's actually changing. So if we're going to write this, we do have to state the state symbols. We still keep those here. We go our lower to higher oxidation reaction. So we went from zinc to zinc 2+ in solution, solid to in solution. We broke up that in one container, and then we had our 2+, gained 2 electrons, change back into our solid copper. And the reason these are important is because that tells us a little bit of how we would start to build it. Here we know that we actually had a solid zinc rod in there and a solid copper rod in there that are actually kind of acting as electrodes to let our electrons pass from one container to the other. So it's just a shorthand. It's a way to write this to be able to kind of describe what's going on. Let's take a look at an example. Let's take a look at an example. Let me enunciate more clearly of how we'd actually start to put this all together. So could we draw a diagram? I'm never going to judge you on your artistic abilities, by the way. Science, dude. Art is not my forte. Let's take a look at an example here where we can draw the diagram, show our balanced equations, our two half reactions, and then write the notation for our half reaction, where we got one half of the cell, that's a chromium bar in a chromium solution. The other half reaction is a silver bar in a silver nitrate solution. Then we got potassium nitrate in the bridge. Measurement indicates that the chromium electrode is negative. It's the anode oxidation relative to the silver electrode. That must be the positive one in terms of our reduction reaction. Cool, let me minimize that for just a second. All right, so here we go. Again, I would never, ever, ever judge you upon your artistic ability when I myself can't draw worth poop. So we got our two half reactions, beaker, 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 beaker. Those are beakers, right? We got our salt bridge in here. I guess we can get real fancy here and kind of erase out. Whoa, too big of an eraser. We can erase out, make that look like it's coming in front of the beaker. Now all of a sudden being all artistic. Cool. So we got our salt bridge there. And then we got our electrodes. We got two pieces of metal with a wire in between. In here, we're going to have a voltmeter. I'm going to volt. Our electrons are going this way through the wire, right? Here's our electron movement. And we were told in the problem, based on what we know right now, told in the problem that we had our chromium, right? That our chromium, this is this solid over here, our chromium metal, Cr, that it is negative relative to our positive electrode, which was our silver, Ag, our silver electrode over on this side. Cool. Now let's think about our solutions here. All of these solutions have nitrate. If you remember from your solubility rules, nitrates are always soluble. These are going to be spectator ions, which means floating around in solution, we don't really care about the nitrates. They're floating around. Yay, that's great. But it's really the ions we're interested in. Here we got our chromium 3+. So if we're thinking about our solutions here, this chromium 3 nitrate solution is going to dissociate in solution. And our chromium 3+ is what's floating around in the liquid. Over on our silver side, we got a silver electrode with our silver ions floating around in solution. So I'm just kind of drawing what's going on, how we actually start to build this. And now we can look at our half reactions. I'm going to go over here and hopefully make this legible. We got our oxidation reaction. We got our reduction reaction. Oxidation is the loss of electrons. We were told that it's our chromium that is losing our electrons. Our chromium is starting at 0. It's turning into our chromium 3+. So we're giving off 3 electrons, turning into our chromium 3+. That's what's happening in our anode on the left-hand side. You'll notice I always wrote from the beginning, oxidation on the left, reduction on the right, so that we always had it the same setup as when we start to do these structures. I know it's weird to think. There's a plan. There's a plan, man. Cool. Our reduction reaction. Well, we got our silver ions in solution. The electrons are flowing over to that cathode. We got to reduce, right? We got to gain some electrons to then turn into our silver. If we think about our state symbols, we're starting with solid chromium, splitting off into aqueous solution. At the cathode, on the reduction side, we got our silver ions are actually going to plate out as a solid on our cathode, on our positive electrode. Cool. So here's our half reactions. They're good. We could multiply and try to get our overall balanced reaction, but it wasn't really looking for that. We just wanted to know our two half reactions, right? And so now we want to get our cell notation. Our cell notation, well, it's oxidation, then reduction, low to high, high to low. So low to high, we said we had, here's our cell notation. We had chromium solid. It's going to react to change into chromium 3+ in solution. Here's what's happening for our electrons on the oxidation side. Our electrons are moving then through our through our wire over to our cathode, where our silver ions in solution are gaining it to turn back into solid silver. So here would be the cell notation for this reaction. If we want to think about our salt bridge, well, in that salt bridge, we had some potassium nitrate in there. So potassium ions, some nitrate ions. If we're thinking about what's going to happen here, we got more and more positives building up in the anode. So our negative ions are flowing down here to keep that container neutral. Our positives are going to come in and replace the silvers that are getting plated out of our cathode reaction. Cool. So here's kind of the whole kit and caboodle. If you want a slightly neater version of this, feel free to look at the PowerPoint. I know scribbles here get a little messy. Thank you for bearing with me there, but it is all here if you want to go back and kind of look at this example as you're working through your info. Or pause it. Here's a better picture if this is a little neater for you. Cool. Follow-up, something to consider. Don't worry about balancing this. I just want you to think about what's going on here. So let's get our half reaction so that we can describe how we go about building this. Yeah, don't worry about the basic part here so much right now. Oh, not that one. Go back. Yeah, there we go. Forgot to hit a button. Don't worry about the basic part right now. We just want to get our half reactions. We're not worried about balancing this all the way. So start with your oxidation numbers. Oxygen's a 2-. I think this is a 7+ on the manganese. Pretty sure that's going to change. 2-, 8 negatives, 2 negatives left over. I think it's changed to a 6+ over here. And then we got our I- going to, this is a 2-, 6 negatives, total of 5+. So we're thinking about our partner pairs. I know my oxygen staying in the 2-, so I didn't bother marking all those. If we're thinking about just our two half reactions here, we're going from a 7+ to a 6+. To do that, we got to gain 1 electron. We're going from a 1- to 5+. We got to lose 6 electrons, right? Sorry, got to think about my charges here a little bit. So for our oxidation, we got our I- changing into our iodate ion. And to do that, we got to lose 6 electrons. On the reduction side then, got our MnO4, 1-, gaining 1 electron to change into our MnO4, 2-. Yes. Now we'd have to do a little work to get these balanced up. We'd have to add some waters here. Let's get it all the way here. So I think I need to, oh, I didn't leave myself enough room. I'm going to need, nope, keep going. Okay, come on, resume. Thank you. We got, looks like we need to get rid of 3 waters, right? So 3 H2Os plus our I-. And then we're going to need 6 H+, I think, to get this balance. Don't worry about the basic part here. We're just getting our half reactions. That's 6 hydrogens, 3 oxygens. We got a 1- charge on the left, a 1- charge on the right. Great, done. Let's see, on our other side here, oh, we're done. Look at that. Perfect. So here are your two half reactions. Think about your state symbols for just a second. If we were going to try to write the cell notation for this, right? What's actually happening here? In terms of our oxidation numbers, right? We're going from I- to IO3, 1-. So we're going I-. It's changing into IO3, 1-. Here's our oxidation side. And then we've got our MnO4, 1-, changing into MnO4, 2-. Here's our reduction side. We're reducing our charge here. But think about your state symbols for just a second. This was aqueous. This was aqueous. This was aqueous. And this one was aqueous. Oh my goodness. Oh my goodness. There's 2 things that we also need to include here. There's a problem here. If we're going to try to send electricity from one aqueous beaker to another aqueous beaker, we need some way to transmit those electrons. We got to be able to stick a conductive material in there. And so oftentimes we would have to, if this was our situation, we would have to add what's called a passive electrode. Some solid that could conduct electricity that isn't going to take place in the reaction. So for this, we could put in, say, platinum. Platinum's a noble metal, is conductive if you got a lot of cash, right? Platinum electrodes. If you're maybe a public school, and you're on a budget, you could also use graphite, carbon, right? Solid carbon electrode, put that down in there. That would let us conduct our electricity. We will also need it on the other side. Fortunately, I didn't leave myself enough room. Sorry about that. I'm going to put it down below. So you just say, I'd also need to put in some platinum, sure, or some carbon, some graphite in to get this to work. Additionally, you'll notice we did have to use some acid. We would eventually change this into a basic solution. But if you had to use some acid to get this to balance, we also show that kind of on this other side as well. We'd say, well, we also had to balance with some acid ions to get this to work as well in solution. So there's some slight kind of nuance here depending on how you're actually going to go to start to build it. We're going to be looking at more examples here as we continue to move forward. I know this is a little messy. I promise we're going to look at a bunch of examples. Just wanted to have an opportunity to talk through these with you before I see you again in class. If you've got questions, feel free to reach out. We'll make sure we're getting it figured out.